Hi everyone, we are going to be talking about Moore's algorithm with updates today, and it's a very interesting topic because you have these set of queries and set of updates, and even though you take them offline, everything works out, the correctness, the time complexity, everything. And there's a special thanks to Nikhil Chandak for this, who actually pointed out a CodeChef problem from the February challenge. I think it's primitive queries. So that's the reason why I actually learned about this, and now finally I got the hang of it. So in case you don't know about the Moore's algorithm, you should have a look at that because that's a prerequisite for understanding this thing. But if you do know about it, then you'll know that simple updates don't work there, because after you've sorted the queries, you might need to redo updates or undo updates. Alright, so let's just take an example explaining that. Now let's say we have some input array for which we need to find for any given range left to right the sum of all elements in them. So left is 4, right is 6, 2, 6, 4 is equal to 12. So these are the kind of queries we'll be answering, and Moore's algorithm is going to take the left block index and the right index and sort all queries based on this tuple. Okay, so what happens if you have point updates over here? Now you have a problem, because firstly, when you sort these queries, you're going to get the order of block size is equal to 3 and n is equal to 8, so block size should be equal to 3. The left block index of these two are the same, so but the right index of this tuple is smaller. So you'll have 2, 7, 1, 8 and 6, 6. Now this is without the updates. If you want to squeeze in updates, we have to do something a little brute forcey. So that is squeeze in updates like this. At 2, 7, how many updates had happened? 2. So those two updates will be done first. So we'll set A to 12 and A1 to -1. Now at 1, 8, it's not trivial to just answer what 1, 8 is, because these two updates had never happened when you were asked to find out what 1, 8 is. So we take that into consideration and we say, alright, we are going to undo the updates. So undo A2 being set to 12 and undo A1 being set to -1. Now you can answer this query. So we have 1 to 8 being answered. But unfortunately, these two updates had happened for the next query, 6, 6. So we have to do them again. Now, again, A2 is set to 12, and A1 is set to -1. And finally, we can answer this query, 6, 6. So, and you see what's happening here. You have, for any given range query, you have to do all the updates again, or you have to undo all the updates again. So in the absolute worst case, for any query, that is every range query, let's say range query, let's say they're q by 2 in number, half of the total queries, and update query is again q by 2 in number, half of the total queries. The multiplication of these two is the number of operations you're performing. So that is q by 2 into q by 2, order of this, which comes out to be order q squared. Alright, that is pretty bad. Order q square is not something that any contest will allow you to, your solution to pass through with that time complexity. So we are looking for something better. Now it's time to understand what the Moore's algorithm really means. It's not just about taking two pointers left and right and finding out the sum query between them. It's more about working with dimensions. So you might have the left pointer, where's it pointing at? That's one dimension. Where's the right pointer pointing at? That's another one. What is the time at which this query came? So what is the index of this query? How many updates had happened before it? How much space is left in this universe, etc., etc. So you have lots of dimensions that you can actually take into consideration. But if you take these three, then you can actually answer for updates also. So with these three, we are going to answer updates. How? Well, if you remember the old Moore's algorithm, it gives free rein to one of its parameters to start from the minimum value and go all the way to the maximum value. In the previous move algo that we knew, the right pointer could start from 0 and go all the way to n. Here, we are going to do something slightly different. We are going to allow time to do that. So time essentially means what is the index of the query, how many updates have happened before this query has come to us. So that could be from 0 to q. Alright, time has free reign except that it has to increase, just like the right pointer had to do. It had free reign but it could only increase per block. Now what? What about right? Right and left will be sorted in such a way that this behavior can be allowed. So the right pointer will be constrained by a block of size b. The left pointer will also be constrained by a block of size b. Alright. So what we have done is we have taken all parameters except one, constrained them into blocks, and given the last one an increasing free reign. So what is the total time complexity that we get out of this? If you notice, now it's not about q square. I mean, the time complexity is no longer q square, because time can go from 0 to q for every left and right block. So the number of left blocks that you'll have, distinct left blocks, are n by b. The number of distinct right blocks that you can have are again n by b. And so the number of distinct pairs that you can have is the product of these two into the amount that the time can move by. So that is now q into n square by b square. So instead of having an OQ square algorithm, we have an OQn square by b square algorithm. And we look at the time complexity later. It's not like we can make the block size huge and then reduce the time complexity. We'll have a detailed look at that and what is the optimal block size that we can have. But important to understand is that we have made a significant improvement over our original algorithm. We at least now stand a chance to have a good time complexity algorithm. So we just said that we are going to be sorting the queries on left index, left block index, right block index, and the time of the query. So what does time mean? Well, time tells you the number of updates performed up to that point. So if there is a range query, it will have a parameter of time which will tell you how many updates have been performed till that range query was actually asked. So we take the original set of queries. At 10, 20, there were no updates till this point, so that will be 0. At this point 10, 19, there are 2 updates, so that will be 2, these 2 updates. There's another update over here, so this query has time of 3. You can call this timestamp if it makes more sense. Actually it does. So timestamp over here is 4. Right, because 3 plus 1 is 4. And so if we sort the queries now, it's not like you get rid of the updates, you keep them in a separate list. And these queries, the range queries will be sorted in this way. So block size is equal to 3, which means the smallest query is over here, 0, 0. So both of them fall in the same left block index. We need to use the right block index now. 19 and 12, 4 and what, 6? Yeah, so this is the first query that we have. 1, 12, 4. Then we have 1, 19, 3. And similarly we have over here and over here. If you notice, the left block index and the right block index of both of these are the same. So we need to find some way to differentiate them using time. 2 is greater than 0, so we take this first. 1, it's 10. So 10, 20, 0. And next is 10, 19, 2. You see that in the Mohs algorithm this would have been different. You would have had 19 coming before the 20. And also you see that in the Mohs algorithm there's a similar thing which is being done. We are trying to constrain the amount by which one of the pointers can move. So over here, if you had more queries, let's say 10, 18, 6 and 10, 20, 7. You can also understand that how it helps you, this arrangement of queries, because the number of updates that you're doing is only increasing. It's not allowed to go back, it can only increase. So in that way, you are giving it a free rein, but only in one direction. So the number of updates go on increasing at most up to a size of q, and these two other parameters, they keep shifting. So now that we know how to sort our queries, let's look at some code. If the number of updates you have done till now is actually less than the number of updates required for this query to be processed, then you need to perform more updates. Well, all the updates after the current time up to the time of the query. Right? Time signifies the number of updates done till that point. So for a query, number of updates done till that query was met in the original order, and current time means the number of updates you have done right now. So you perform the update and then you increment the number of updates you have done till now. Alright. Very similar to that is if the number of updates you have done till now is greater than what was required by this query, then you need to perform some undo operations. You need to undo all the updates which are in excess. So till this condition is true, you will perform undos for all the updates in current time. So current time will be decremented and therefore you will be getting rid of the excess updates. This is the excess code that we have compared to the standard Mohs algorithm. After this comes in the normal, if the left index is greater or lesser, then you move it around and so with the right. Let's take an example now. We have this set of queries with us, and our job is to find out, just like in the old question, for a given range left to right, how many elements have frequency greater than or equal to 3, and based on that we give out the count. Okay, and we also have point updates now. So how do we process this? Firstly, we have talked about the tuple that we really want, which is left block index, right block index, and the timestamp. So these two can be calculated. What about the timestamp? The timestamp is the number of updates that have been performed till this point. So over here it is 0, no updates yet. We perform one update here. So after that this query comes in having timestamp 1. 4 more updates happen here. So this has timestamp 1 plus 4, which is 5. Now if you sort according to this tuple, you get, so the first left index is 2 and 1 will fall in the same left index because block size is 3, because the array size is 8. So that will be, now we need to look at the right index. So right index of this is smaller, right block index basically. So that is 1, 4, 5 as your first query. You have 2, 7, 1 as your second query. And your last query is 4, 6 and 0. This is interesting. What we need to do is process these queries in this order. And look at the first query. It has 5 updates to be performed. The current number of updates you have performed is 0. So we need to do 5 updates before we can actually answer this query. So that's exactly what we'll do. 5 updates. So let's go to the first update. A of 6 becomes 2. So I'm writing that in blue. A of 6 becomes 2. But that's not the only information that you need to have. What if you need to undo these updates? So quickly, before I forget, I'm going to make this back to 1 and set these values according to what the previous value was. So A of 6 becomes 2 was previously 1. So I'm writing that down in brackets. A of 1 becomes 7 was previously 1. A of 4 was previously 2 becomes 1. A of 0 was previously 0 becomes 3, and A of 3 was previously 2 and becomes 1. Alright, so that's good. What if you had an update over here which said A of 3 is set to 6? Well, what you need to have is a pointer. So over here, whatever value comes actually points to whatever was there previously. A of 3 is previous, which is over here. What A of 3 was set to. So that will be 1 over here. And that's how you set these previous values. You check whatever is the current value and set that to previous. In fact, in the code, it's much simpler than it looks over here. So you can have a look at that over there. Okay. Let's process these queries then. Perform 5 updates, huh? Should be simple. Like we said, A of 6 changes to 2. A of 1 changes to 7. A of 1 changes to 7. A of 4 changes to 1. So that's here. A of 0 changes to 3. That's nice. And A of 3 changes to 1. Okay. Okay. Let me just confirm that. A of 6, A of 1, A of 4. Yes, now I need to use both hands. 0 and yeah. So this is fine. Now, we can actually answer this query now. So 1 to 4 is what we need to do. Our left index is pointing at 1 first. And so is our right index. Frequency of 1 is, the value at 1 is incremented. So f of 7 is incremented, that becomes 1. It still hasn't hit 3, so count is still 0. What about, now the right index has to be incremented because it's not equal to 4. So 1 is added, f of 1 is set to 1. Our right index is now pointing here. Then it starts pointing over here. F of 1 is set to 2. It's then set over here, and that's equal to the right index, so we are done. F of 1 is set to 3. That triggers this condition, and count is set to 1. So for this query, count is 1. Alright. What actually Mark is here. Teja Mark is here. Anyway. Okay. 271 is the next query that we need to look at. But there's just one update here. So we need to roll back 4 updates because our current update counter is actually 5. We should have incremented the update counter when we were actually doing the updates. So this is now set to 5. This is 1, so we need to actually roll back 4 of the updates. So our current update pointer is over here at 5. Start rolling back. A of 3 has to be rolled back to what value? 2. So A of 3 is rolled back to 2. But that's not all. This value was 1. I'll just write that down. The frequency of 1 basically got decremented and the frequency of 2 got incremented because this value falls in the range that we are looking at right now. So this index j falls within left and right, and therefore we need to perform an operation such that this is allowed. So whether it is actually making an update or undoing an update, it doesn't really matter. Both operations are symmetrical. We need to check for this condition whenever we are doing it. And whatever value was there earlier, like f of 1, that needs to be decremented to 2. And these two are redundant. Yeah. And it's being set to 2. So f of 2 has its value incremented to 1. Now the next update. We have undone this. That's great. By the way, current updates is now set to 4. A of 0 is rolled back to 0. So this becomes 0. Is that falling in our range? No. So nothing to do. That's nice. Finally, let's work. And current updates becomes 3. A of 4 should be rolled back to 2. Does it fall in our range? Yeah. Yeah, it does. So first we decrement the frequency of this element, f of 1, is set to 1. And what is that set to? 2. It needs to be rolled back to 2. So this element has its frequency updated to 2. Okay, we are doing reasonably well. We need to go back here Current updates are what, 2? Yeah. So we need to go all the way back here, but we aren't there yet. So roll this back. A of 1 is set to 1. So f of 7 had to be decremented, that's over here. A of 1 needs to be incremented, so that becomes 2. And you see that this is consistent with what we have. Now current updates needs to be decremented because we have rolled this back and we are pointing here. We have just one update, which is exactly what we wanted. These are the frequencies of the elements. None of them are equal to 3, and count is therefore, it remains 0 basically. It didn't hit 3 here. So yeah, count is 0. Well, count became 0 actually because f of 1 was 3, but then when we made it 2, count should have been decremented, and so the answer for this is 0. Alright, the final update, the final query actually, and thank God it just has one rollback. So let's roll that back. So yeah, first let's roll the update back. A of 6 becomes 1. A of 6 becomes 1. Current number of updates is 0, which is what we want. Current number of updates is pointing to nothing. And what do we need to do? Yeah, A of 6 became 1, which was 2 earlier. So A of 2 has its frequency decremented to 1. Or does it? No, not really, because it didn't fall within our range. So we don't do anything. A of 2 is still, f of 2 is still 2. So yeah, no update in the frequency array. Now all we need to do is perform the normal Mohs algorithm, which is move from the left index up to 4 and the right index up to 6. So left index needs to move up to 4. That is going to decrement the frequency of 1, 1, 2, 2. So get these guys out. They have frequency 0, 0. And I'm fast forwarding a little bit, but that's because this is the standard Mohs algorithm. That's where left is pointing now. What about right? Right is going to point to 6. So over here we have right pointing to 6. And when it does that, it grabs these two elements and increments their frequency. So that will be 1 and 1. Doesn't really matter in terms of count, because count is never incremented till you hit 3. So count for this is still 0. So in fact, if you look at this, this was our original array, and the count within this range would have been 0. So this makes sense. And so this example is solved. The time complexity of this is quite interesting. There are 3 things we need to look at. One is how much the right pointer moves by. Second, how much the left pointer moves by. And finally, what is the timestamp movement for all given queries combined. So let's have a look at the right pointer first. The right pointer, when you have a given left index, left block index for you, the right pointer can move freely in an increasing way. So the right pointer might start at 0 and go all the way to n. In fact, this won't be correct because the left pointer will have a non-zero index more often than not. But let's take the absolute worst case scenario. Let's say the right pointer is going all the way up to n from 0. So that is n computations for every fixed left block. So that is into n by p. Okay, but that's not the only thing. The right pointer for a given left block. So now let's say you have a fixed right block also. In this, your right pointer might be starting over here. So you went all the way here. That is b computations. Plus, in the next query, your right pointer has to go over here and point here. So that is b. In the very next query, again you have to go all the way back here. This is possible when your updates are coming in a very weird fashion. So every time when you're over here, you have the minimum number of updates. You have the second most minimum number of updates here, then the third most here, fourth most here, and back and forth. So you have to do a lot of computations over there, and basically b for every query. So in total, for any given query, you might have to jump by B. So that is in total Q into B. This thing is a little difficult to get your head around, but if you think of it, every given query, for any given query, the right pointer is moving by at most B. And so the total complexity of that is Q into B, and this is for every block you have N into N by B. Alright, now let's have a look at the left pointer. The left pointer analysis is very similar to Moore's algorithm. You have for every given query at most movement of B, because the left pointer is constrained by that block B. So that is equal to Q into B. Right, and what about timestamp? Well, in fact, left pointer is Q into B plus N, because it might go all the way to the right before hitting any block. So yeah, you'll see that that doesn't really matter. What about timestamp though? For every left index, for every left block, and every right block, the timestamp has free movement. So timestamp has free movement from what? 0 to Q. That is Q values that it can take for every left block, which is this in number, N by B, and right block. So for a distinct pair of left and right blocks, it has free reign up to Q. So these are the three parameters that we have. Finally, the order time complexity we'll get is order of QB plus N square by B plus QB. In fact, we don't need this because QB is already there, and order complexity, this term won't matter. Now we have Q N square by B square, and this is the complexity that we have. Alright, do we really need this term? If B is equal to N, this term is still greater than N. If B is equal to 1, this term is much greater than N, so we don't need this term, N. Do we need QB? What if B is equal to N? Then this will be N square, and this will be Q, so we'll need this term. What if B is equal to 1? Well, Qn square will be greater, but we can't say. Basically, this term might be useful. What about this term? If B equal to N, this is equal to N, and if B is equal to, yeah, there will be Q and N over here. So Qn will be over here, and there will be N over here if B is equal to N. If B is equal to 1, then this will be Qn square, and this will be N square. So this will be smaller than either this term or this term. So we can get rid of this term. N square by B square won't be required. Alright, and this is the final time complexity that we have. QB into plus Qn square by B square. Alright, so let's write that down a little more neatly. Order of Q in common. What is over there? I think N, yeah. No, B. Okay, wow. And we don't need a Q over here. Okay, so this is the final time complexity that we have. How do we analyze this? Well, we can differentiate it and find out what is the best block size that we can have. So let's do that. Differentiating this term. Q is a constant, so we don't really need to take that into consideration. B plus N square by B has to be minimized by differentiating with B. So for an extremum, this must be equal to 0. Differentiating, we get 1 minus N square is 2 over here. I'm sorry, there's a square here. Okay, so yeah, minus 2 by B cube is equal to 0. What we then get is B cube. I'm trying some hocus pocus here. Yeah, equal to 2n square, which in turn gives us that B is cube root of 2n square. Now, if you're not bothered about too much accuracy, that's equal to n 2 raised to power 3, which tells you that this is what your block size should be, and that gives you the number of blocks in turn should be equal to cube root of n raised to power 1 by 3 basically. So if you have these many blocks of size n raised to power 2 by 3, then you're looking for an optimal kind of solution. So that's it for Mohs algorithm with updates. In case you have any doubts or comments, please leave them below. I'll be sharing the code for the problem that we talked about below. And this is a pretty advanced topic, so in case you have any suggestions, or if there are any mistakes that I made, then please feel free to point them out. I'll be working on this problem called primitive queries from the CodeChef Feb challenge. So that should come out next. In case you want a notification for that, you can subscribe. And yeah, until next time, see you.